and welcome to SciLux, the podcast where we talk about scientific developments and technological changes in Luxembourg. And in today's episode, we welcome the very special guest, as usual, Dr. Jan Thoemel, who is the head of the CubeSat lab at SnT, so the Interdisciplinary Center for Security, Reliability and Trust at the University of Luxembourg, and who will tell us a little bit more about the small miniaturized satellites and his research relating to Mars, as well as many other subjects related to space. Hello and welcome to SciLux. Our guest today is Dr. Jan Thoemel. Thank you for joining us.
It's my great pleasure to be here. I say hi to all the audience.
Today we're going to talk about all the different subjects that you have been interested in and you've researched in Luxembourg and beyond, of course. And what I would like to start with is one of the interests, so the nanosatellites and small satellites. So I know that you are behind the CubeSat project in Luxembourg with students and your own research. So tell us a little bit more about CubeSats first.
So CubeSats are very, very small satellites. The concept has been invented like 15 years ago, so it's not too young anymore. And they followed this trend of miniaturization. We know that from our cell phones. They used to be big and became smaller, and then they became more and more powerful. And somewhere with this trend, people discovered in the United States, unfortunately, again in the United States and not here in Europe, that also satellites could be miniaturized, could be made smaller, could be standardized, and then due to the low cost and the standards, the easier engineering, that university teams, for example, can have their own CubeSats in orbit, and then not only to study but also to experience spaceflight. So this all happened 15 years ago, and it was a huge success. Many universities all over the world launched their satellites with their own ideas. And it is, for me, impossible to even track who is developing what kind of new mission there. And just like with our smartphones, because now there's such an abundance of satellites, people come up with totally crazy ideas we didn't think of that are possible. And that's very, very exciting to see.
Exciting and also dangerous, because when I think about satellites, of course, I also think about commercialization of space. And of course, Elon Musk and SpaceX come to play as well. And his satellites that are basically populating more and more, taking more and more space. And that's, the second, let's say, phase of the whole development that maybe most probably is not that exciting for scientists, is it?
So that's it's a very, very good point. We have to be careful that space remains sustainable for all following generations. However, I would like to say something to that. We do take care when I do this kind of research, and we intend to launch within a year or two our own CubeSats. This sustainability is implemented in our DNA, and it is also implemented into laws and regulations that we follow. So I need to explain this because I want that people have the right impression on this. When we go to space, we think of vacuum. However, if you go not too far to an altitude of, say, 500 kilometers, where the majority of satellites are, we still have a bit of atmosphere. And this atmosphere slows down a satellite. And you can do the calculation, how much slowing down does happen there. And then you can calculate when is your satellite slowed down so much that just falls back on Earth. And so there are laws and rules, and we try to even be more careful than the law. We put them into an altitude where they will be falling back to Earth in a limited time. And we can do the calculation how much time is needed to have a sustainable space. And we do this. And when they fall back on Earth, we can safely say that these satellites entirely burn 100%, they completely evaporate. And that's also not a major problem. You have to imagine that there is every day many tons of natural materials coming back to Earth as meteorites. We make good wishes at night if we see them. So the kilograms that come down every day to Earth due to burning satellites, it's very, very little to the material that comes naturally. So we do take care that space becomes sustainable and safe. It does not mean that we have to stop thinking of it. Not at all. And you're quite right. Particular SpaceX, they launched a number of satellites that we could not have imagined that when we started to think of space safety. So we need to continue with this calculation and our estimation when what altitude can we launch satellites so that they safely come down on their own, or, and that's what is also done, that we deorbit them with their propulsion system, with little rockets that are attached to satellites. So we absolutely take care, and when we launch our CubeSats, we make sure it's safe.
That's a very good point. And I guess also with CubeSats, as they are quite small, it's also a different discussion, right? I mean, they are not meant to last. They are just supposed to do their calculations, get the data, and then exactly burn once re-entering the Earth.
Yes. So this is part of what we research and also what we teach. What is the purpose of that mission? And there are so exciting ways of using satellites. How long would they function in orbit? How long would they stay in orbit? And then how they come down? An interesting mission could be to launch satellites to track other satellites, to exactly know where are the satellites, how do they fly, how fast do they come down, and kind of a police mission. That would be actually very interesting to study. There are, we're scientists, we have plenty of ideas. This might be one that furthers the cause of sustainability of space.
So could we say that in this case, paraphrasing, sky is the limit? Is there any limit on what you can use the CubeSats for? Is there any regulation here or not?
This low Earth orbit space, is relatively low, is regulated, has always been regulated. So we would need to, for example, tell the authorities that we intend to launch, and they have a database in Luxembourg. And every country has one, and the United Nations have a database. So we need to notify this so that others could know where our satellites are. Beyond that, there's not too much regulations there. Now there's, of course, there also say there's rules. What if my satellite falls into another satellite and destroys them? There is laws covering this aspect, but then it's not too much regulation because these laws are old and were not made for so many satellites. There are, of course, limits, and that's the physics. Yeah, once you know how high you are, you have a certain speed, and that's the laws of physics nobody can break. So you go with a physically defined speed around the Earth. Or also, we have seen the launch of the James Webb Space Telescope, which is a huge satellite. And it has a reason why it's huge, because the physics that clearly say if you want to have very accurate images, you need to have a big spacecraft. So then that means a small satellite like these CubeSats that cannot make super great resolution images. With a constraint there. We've seen that also in our cell phones. Modern algorithms, machine learning, can help us to get much, much better pictures even out of small satellites than we would expect from a normal camera. I hope to see a lot of great imagery from very small satellites due to these modern algorithms.
Of course, and it's only going to get better, obviously, with all the technological changes that we can't predict at all. But just going a little bit back, a step back. First of all, the size of a CubeSat, so that our listeners know more or less. If I'm not mistaken, that's 10 by 10 by 11 centimeters, something like that?
So the very rough numbers are quite, as you say, is 10 centimeters times 10 times 10, and say maybe some, let's say, additional little volume there. Then it's about 1 kilogram, and it's also about 1 watt of power, because that's important in space, how much power you have. You cannot recharge your battery on a gas. You cannot recharge your batteries on a gas station. You need to have solar cells to produce power, and that requires size, surface, that defines how much power you have, and then it defines what you can do. And again, we have a physical limit there. If you produce a lot of data, very accurate images, and you can clearly link the amount of data that you can download to Earth to the power that you have and that you create with the size of the satellite. So that's again the laws of physics, that you cannot break. Surface means power, means the amount of data you can download, and that's very exciting, and it's what we study and what we teach.
Okay, so now we have the sizes. Then, if I want to send it to space, I need a deployer, right? And that
Yes.
deployer is it like different places where I can send it from? I need to have a cooperation with the launchers. How does it work?
Yeah. So the very big innovation in these CubeSats was actually not the standardized size of 10 centimeters times 10 times 10 centimeters. It was something else. It was that they discovered 15 years ago that almost all rockets have some what we call dead mass. They have some ballast. And you need that because the rocket has a certain performance, can bring to space, say, 1 ton, but a satellite is never exactly 1 ton. It's going to be less, maybe 700 kilograms or so. That means there's always some dead mass. And they discovered, why don't we use that mass to launch satellites? And these rocket builders, for example, the European one, Ariane Space, they said, it costs us almost nothing. We can attach some satellites there. But, and here it comes, these small satellites, when they are built by universities, they are very often experimental satellites. So they may not be extremely reliable. And then those rocket builders or those of the big satellite are a little worried. So what they said, okay, if they're worried, then we launch these CubeSats from inside a box. And so we may not require the satellite to be very reliable, but only that box that surrounds it, that protects it. And so that was the reason why CubeSats were so popular, is because they were now, everybody could build them, even if they were not, did not have 20 years of experience, because the box around it was protecting the rocket and the main satellite, the James Webb Space Telescope, from a potential breaking up a CubeSat. But that was the beginning, and then this standard became so popular that today, to be frank, CubeSats are very reliable. Today, we may not need this box anymore to protect the main satellites, but it is now an established way of launching satellites.
And when it comes to the design itself, how much can I just buy on the market? Because I understand what you decide to use it for. That's your ideas, your, different electronic equipment that you put inside to measure certain things. But the cube itself, so the radiation protection and everything else, how do you get that? Do you also design it, or can you just go and buy it on, Amazon?
That has developed or evolved at light speed, to be frank. For persons like me who wants to build satellites, we have been overtaken by a market providing such subsystems or systems at enormous speed. So today, even for university, it may not be useful anymore to design and build the entire satellite, but to focus on what you want to have as your key competence, and the rest you buy it. And you could indeed, there exist websites which are kind of an Amazon, and you just buy solar cells and maybe a structure. But you can go beyond. You can go there and say you want to have a satellite that has a certain hole for your own, what we call a payload, the sensor. Imagine you want to have a CubeSat mission that has your camera. We build a camera to observe Luxembourg. Then you can go there and say, okay, can you make me please a satellite that can accommodate that camera and send it to me? And you can go beyond. You could even just develop a modern algorithm, artificial intelligence, machine learning, and say to a company, can you please build me a satellite, put on it my software, build a satellite with a camera, put on it my software, launch it, I pay you when you prove that this satellite is in space and working in space. Well, that's what's called a turnkey solution. So this market has matured and evolved enormously. That is enabling universities now to focus on something they really want to be excellent, world excellent in. That could be, I mentioned a camera, it could be a software, or it could be also on super low weight structures. Wherever you want to be scientifically excellent, you could focus on. And that developed at an enormous speed.
And that's what also makes you actually work right now in the CubeSat lab at university. And you can also focus on just teaching the students, developing certain things and not everything, right? Because the project I know that you worked on is the Goldcrest project. Can you tell us more about this?
So indeed, the first group of students, they have developed the Goldcrest project, and it has been followed up by the second cohort who named their mission Daffodil, which is the flower that is, it's a narcissus, which is impressed by its own reflection. It has a story because both Goldcrest and Daffodil use a modern Earth observation technique. So what I do with my students is I make them actually designing the mission and the satellite. But instead of now soldering in the lab the different hardware components, what I make them do is do what we call system engineering. I ask them, please determine how much power do we need, and then go to this Amazon on the internet and select those available components that suit this purpose. If it exists, if not, then we'll have to design it. And that's follows this system engineering trend follows exactly what also, for example, car manufacturers do. The car manufacturers don't build the entire car anymore. It's way, way, way too complicated. The big brands, they buy subsystems, they buy the seats, they buy the wheels from different components, and then they just put it together. So I hope that is also useful for the students, even if they don't stay in space, that they understand that the system engineering that is, in essence, assembling first virtual and then in reality, is a way to address highly, highly complex technical systems, such as satellites or also cars. And it would apply to many other technical things too. Planes, whatever is complex is today done in a system engineering approach, which is really, really complicated. So that's what I do. I ask them to do the system engineering to determine how much power do we need, how much data do we produce, which then translates into how much power we need for the communication, which translates into how much data they can transport, and then also do some certain astrodynamic calculations, for example, at what altitude, what kind of Earth observation can we do. And I use a method that is called reflectometry. That's why the second cohort called their mission after this narcissus, the daffodil. These CubeSats, they don't have a camera, but they have another device that receives the reflections of GPS signals. So we have a GPS receiver in our phones and we use it for navigation. But some people discovered like 10 years ago, oh, there is something else we can do with it by not using it for navigation, but to receive the reflection of that GPS signal after it was reflected off the Earth. And this reflection, this GPS signal, when it has touched the Earth and then arrives at the CubeSat, was changed by the reflection. It's like you look at the mirror and sometimes your mirror is not good. Then you see your image is less good, or it could be a colored mirror, then you would see in your image there is something, you would look at yourself differently. So from this reflective signal, you can determine this property of the surface at the point of reflection. And that's a very modern method to observe the Earth. And it has, of course, also disadvantages, but a lot of advantages. For example, if we had a camera on our CubeSat, it would not work at night. It would not work when we have clouds. But the GPS signal, that works also at night. That works also during cloudy times. So you can see all the time. And that was one of the most important aspects why we chose that. It's very, very small. I mentioned it on a CubeSat. We cannot put the telescope of the James Webb Space Telescope. We need to find a sensor that is small. And that is actually possible with this reflection payload or reflection method. So that's what the students did. They put together, and then they called it Goldcrest after a bird, Luxembourg national bird. It's important to give it good names so that people remember and hopefully have a good memory to it. Yeah, and it would be my aim to advance this design, then to launch it.
And you said that students were learning from this, the preparation, so how to measure different distances and the need for energy and everything else. But then also there is the aim of the satellite. And I know that the Goldcrest project the idea was to measure the moisture of the soil, right? Where does that idea come from? Why is it this particular one? And is it going to develop throughout the cohorts of students, or?
So because it's the method uses the reflection, it is very sensitive to the property change of the surface on whether it reflects well or not. And water is here the key component. A watery surface reflects better than a dry surface. So that's why the method is excellent for determining water content. So the first one cohort, they were determining how wet is the soil. And there are numerous applications for that. So you can imagine a farmer could possibly use the information from a satellite on how wet his fields are instead of going out. Now, that's of course only useful if the data is cheap. If he has to pay €1,000 a day for knowing how moist or how wet his fields are, he's better driving out. But if it comes at a low cost, then he may do that. And in order to make it cheap, you have to be small. And that's the CubeSat is perfect for. Measuring water has really many applications. So you could use it for farming, but also it's simply the hydrological cycle of the earth. That is, water is cycling, right? It rains down, it goes to the rivers, it goes to the sea, it comes back as clouds. If we have a good understanding of this, we can better understand weather, we can better understand climate change. You may remember we had these flash floodings last year. The economic impact was enormous. Many million of damage were created. And if we could contribute to better understand how the hydrological cycle works, how climate change, we could do a contribution to avoid this kind of damages. So that was the first, was soil moisture. The second year, they were looking into how the change of certain water bodies, lakes, or rivers, swamps. That's important. For example, in Siberia, we have now the permafrost melts. So we have now more swamps. We have larger lakes. So we'll be able to monitor how climate change happens there, for example, in Siberia. In the third cohort, don't tell them, they don't know yet, but we want to, again, address water, but I want to investigate with them then ice. Also, highly important, for example, when it comes to climate change, we see the glaciers recessing. If we had a scientific, reliable, but also cheap method, gave a data that has not been available before, maybe at a low cost, so that we better understand, for example, climate change.
But then you will not test it, really, because you said that maybe one day we will launch this CubeSat, but every year with the students, it doesn't finish with a launch.
So that's correct. So a CubeSat, even though we studied with the students, in the end, as a full satellite, it's a highly complex system. What we cannot do is just take the drawings and just launch it. Even though many things are simpler with CubeSat, it remains a full satellite. It's a highly complex system, so we couldn't do that. However, the idea here is that the first cohort did the first studies. The second cohort, who then were not looking into soil moisture but into water bodies, they were building upon what the first group of students has done and have made a very nice simulator. So their design method was way more refined. So we have a much better understanding now how such a satellite would work. And this will be with the next cohort the same. So each time we improve, better understand the engineering, but also the scientific aspect. And we are now in a position that this is quite mature. We'll just have to find a bit of money to do that. Yeah, but the discussions are going on. That is not even a CubeSat. It's not a piece of cake. So that money needs to be spent with a good reason, responsibly. So we'll have to have a bit of a discussion on if we are really ready for building it and what purpose it serves. However, I can promise you we have that discussion.
That's great. So I'll be following up on that project for sure. And when we talk about CubeSats, I think this is a good moment to move on to your other interest, because I know that CubeSats were also used in one of the travels to Mars, right? Was that the first CubeSat project, the Evie and Wally CubeSats that went to Mars?
I know them under the name Marco.
Yeah, Marco, exactly. I think they were called Evie and Wally, but never mind. Marco project. Yes, that's what I meant.
Yeah, okay. Then the project was Marco, and then the name of the two satellites were there. Yes. So there were two satellites two CubeSats, which were rather big. Now, we talked about 10 centimeters times 10 times 10. They were a little bigger. They were 10 centimeters times 20 times 30, which is still not big if you're considering the vast distances to Mars. And they were doing a flyby. That means they were launched together with the major InSight mission, I think, of NASA.
Mm-hmm.
Again, with the same principle. They had mass left over on a rocket, and then they were launched. And then the satellites were separated, flew past Mars, but they did neither enter into the orbit, nor did they land. And that is because if you want to land or enter the orbit, then you need to have a very performant propulsion system. And that takes a lot of volume, and also that's also expensive. They did not have that. Yet it was a great success from these very small satellites to that they allowed to relay some data to Earth.
Yes, exactly. So before you tell us a little bit more about your interest, as I said, about Mars itself, I would like to pause here for a second and ask you to move on to the usual pub quiz style question that we always have in our podcast. So I know you prepared something for our listeners. Could you tell us what the question is?
So I want to know from the listeners, what greenhouse gas is the atmosphere of Mars made of, and why is it not hot there?
Sounds very interesting. So as usual, we'll tell you about the answer at the very end of the podcast. But now, as I said, let's move on to different things about Mars, but of course not the atmosphere. We have to be very careful not to reveal the answer. But of course, I mean, there's a lot more to this. So I wanted to discuss Mars because I know that the other research and other the field that you are interested in is travel to Mars, and particularly the problem of landing, if I may say it like this, the problem of the so-called blackout. Am I right? Can we call it like that, or this is just
Correct.
a jargon word?
If I may make the link to the CubeSats have enabled a business in space. Now they became mature. They were in the beginning were a university and experimental CubeSats, but now people make business with it, and that is important in Luxembourg. And I love the principle to make business in space, because it will help the economy. It will generate tax, help us all, but it also helps the science. So if we were to have an astronomy mission which does not immediately give a benefit, a financial benefit, commercialization will develop technology that we can use for science. And that is an unlikely connection to the Mars research that we do, is that while CubeSats can create commercialization opportunities in the short term, or right now, the next big step in Luxembourg is have a business into interplanetary missions. Now, for example, to the moon, and next stop of the bus or the train would be then Mars.
And space resources, right?
And we talked about space resources, so quite right. And the re-entry with the blackout, that's the very last step. And before we get to Mars, we could go to Mars maybe with using space resources, which may be commercially obtained. Maybe somebody will build a gas station around the moon and just launch with a now smaller rocket towards the moon, refill, and then fly to Mars. So there's a very long-term vision of business in there, which I love, because science missions to Mars may be cheaper in the future because we don't have to launch the propellant off the surface of the Earth. No, we just have a smaller rocket, cheaper rocket, go to the moon, refill, and then go to Mars. And that's part of the research that we do here with the students. And that's pretty complicated, because the path to go from Earth to the moon is complicated. You need to find not only the path, but also the right time, because then you need to wait a bit around the moon, then you go to Mars. And there also, you may know, there are only every 2 years opportunities to go to Mars.
Because it's closer, right, at that moment. So it's the shortest possible time frame.
Yes. So that's what we study. What kind of propellant can we find on the moon? For that, how much do we need? And most likely, this propellant will not be so performant. So then, again, this study to the mission to Mars will be more complicated, because now we have maybe a lower performance satellite mission that may take a bit of longer time, or may not even be possible. So we study this, and I'm learning every day here from my students sometimes when they study this. And the very last step is then how to get to the surface of Mars, which is related to, say, a landing on the Earth. And what is known that when you enter into the atmosphere of Mars, but the same would apply to the Earth, is that the gas, the atmosphere, which I will not reveal what it is, will get very, very hot. And when it gets hot, then you will have an ionization. It will become a plasma. And that's not good if you want to communicate to your spacecraft. It just prevents it. If you see movies of Apollo, for example, or the space shuttle, there's some time when you cannot communicate to the spacecraft. That's because of this plasma. And that has not been well understood. The very, very basic physics may be, but not the practical aspects. And what we do here is to apply very, very modern methods of satellite communication engineering, better understand why do we have these blackouts. Well, we know it's a plasma, but how exact? And what can we do? There are different possibilities to avoid this problem of communication blackout. Maybe just put more power, change the frequency, change direction. And then with support of the European Commission, what we study is maybe we can put a big magnet, an electromagnet, on that spacecraft. And that is possible because now we have these high temperature superconducting magnets. So when we say high temperature, we mean minus 150 degrees. So it's quite cold, but these superconducting magnets usually required in the past minus 250 or much, much lower temperatures. So now we are at the level of temperature that we could actually create inside a spacecraft. Then we have these magnets and we could create a very strong magnetic field and then to change this plasma. And then we could possibly avoid this communication blackout. Now, is that actually important? Sometimes I speak to people, you fly 6-7 months to Mars, and then for this 1 minute, you make such an effort to allow communication. Is that useful? Absolutely yes, because when you fly these 6 months to Mars, absolutely nothing happens. It's quite frankly, it's quite boring. Everybody just waits. When do we arrive? We are in space. If the sun is not extremely active, really nothing happens. Usually they switch off the satellite or the spacecraft and just wait. While in this 1 or 2 minutes, when you re-enter into Mars, you have enormous decelerations, enormous forces, enormous heating. Could be megawatt of heating per square meter. So a lot of things can go wrong. And it happened in the past that something went wrong. There was an ESA mission called Beagle 2 some 15 years ago, and it was never heard of. And that's tragic because even if it failed, but we know why, then we have fulfilled half of the mission because that's why we do it. We go to Mars to advance this technology. So we want to know if things work, but also if it's not working, because then we do better. So it's really tragic not to know why it failed. And we cannot know why Beagle 2 failed is because we were not able to communicate during that extremely critical mission arc. So we're working on this with very modern methods here with the colleagues who were not doing traditionally CubeSats or missions to Mars, but they have some modern methods to better understand how this communication works in the presence of plasma, in the presence of a magnetic field, and then to overcome this problem.
But it's the beginning, isn't it? Right? This is just, you can't really say where you're going. It's the beginning of the project or of the research.
We know the principles. We know that a magnetic field has a certain influence on the flow and on the communication, but we don't know how to use that influence properly. So we have to figure out, okay, what magnetic field strength, for example, which shape of the magnetic field, where the magnetic field, in combination with other variables that we have, how to optimally use that technique to overcome this radio communication blackout.
And you also have to create the plasma.
But we do computations. So no, actually, you're quite right. So we do the exact research that we do here at the University of Luxembourg is we take computations of plasma and then use that results of this plasma computation to do some computations for our radio communication. Now, that would be still very, very theoretical. You're quite right. There's an institute in Belgium and also one in Germany who can create this plasma. or they have a wind tunnel that can create gases. In the case of Earth, it would be air. They can heat it up to 10,000 degrees. And then you have this plasma. And then you have this blackout. And so then we also do computations not only for the re-entry into the Mars atmosphere, but also in that facility. And then we can say whether our computations are actually correct. It's going to be pretty challenging because 10,000 degrees hot air or the other gas of Mars is very hard to control and very hard to quantify. Yeah. So we know the principles, but we do not know how far we can go.
Okay, so the only thing that remains is again to keep our fingers crossed. Yet another reason to check out on what you're doing right now and what are the results. The CubeSats project, the Mars project, I'm sure a lot of other things. Unfortunately, we don't have that much time left. I mean, I was sure that probably if I schedule 1 hour, I will want to talk for 3 hours because there's just so much going on and I'm so interested. But yeah, well, definitely we will have to meet again, hopefully soon, to discuss other things. And whenever there is something interesting, I will definitely contact you to discuss it. But just first of all, before we wrap up, I would like you to give us the answer to the question you asked.
So I asked for a greenhouse gas, and it's actually a very boring greenhouse gas, is the carbon dioxide that causes us a lot of trouble here on Earth, but it's abundant in the Mars atmosphere, but it's in the end very little. The atmosphere is very thin on Mars, and therefore it's now thin, and therefore Mars is very, very cold. That was different in the past when the atmosphere was thicker, and then also Mars was hot, maybe as hot as on Earth.
So why do we actually say that Mars is the best bet for a human mission? Because, well, it's still very far away from Earth's atmosphere.
Yeah, for a number of reasons. It is relatively close. I say it's cold, but say approximately it's between, depending on where you are on the equators, maybe between minus 50 degrees and plus 20 sometimes. So you find places in Siberia, I come back to Siberia, that have the same temperature range. So it's not too extreme. In other planets, we have a much more extreme situation. So we could actually, an astronaut could walk on the surface. It's not too far away. We know that the history was favorable to life. So it's also a good goal to go there. If we dig there deep enough, we may find extinct life, maybe bacteria only, but maybe even something more evolved. It's a good goal. It's relatively normal conditions to compare it to Venus. Venus on the surface is hundreds of degrees hot and with an enormous surface pressure. So an astronaut could not walk on the surface of Venus. And the other planets are sometimes made of gas. You cannot walk at all because they're not solid, or they're extremely extreme, very, very hot, like the moon of Saturn. Titan is extremely cold and has liquid methane on the surface. So we don't know if we can just walk there. So these are very, very extreme conditions. So still, going to Mars is very, very difficult, but it seems to be possible with the available technologies today. Let's achieve that, and before we go to these extreme other planets or moons.
What I can say is that I hope my podcast will still be there, so we can once meet and you will tell us a little bit about the mission and the achievements, hopefully with Luxembourg on board, and your research too, with the magnet and, no communication problems and all the successes. But yeah, we'll have to wait a little bit, right? What is the time frame we are looking at? What do you think ambitiously? When can it happen? I know I'm asking you to predict something that is impossible to predict.
So we will see people walking on the moon in, say, 5 or 10 years. And that's a conservative calculation. Mars, it's more difficult. It could be 20, 30, 40 years. But I think Hannah, you and I, we will see this. And that's great.
Absolutely. The sad bit is it's not going to be like, in the past, watching on TV, everybody sitting around. I mean, I have a feeling that nowadays, whenever there's a achievement of landing somewhere, whatever, it doesn't get that much attention as it used to in the past. I mean, the moment when a human landed on moon, it was really like everybody was watching it, right? And now it's just like, yeah, there's a stream of somebody going somewhere, but who looks at it.
It's a bit. You are quite right. It's a bit hidden in the stream, but I know for sure people are very interested in space. Of course, there's a lot of competing things that are going on, in particular last 2 years. Naturally, people had more difficult questions to tackle. But I see always people interested. When I am in Luxembourg, I do sports with friends. They always question me, what is this all about, the space stuff. When we have a day of open doors, an open day here at the university, many people come and look and ask questions. Sometimes even critical questions. People ask, is that all useful, what we do? I know for sure people do care a lot.
And with this positive thing, the only thing I can say is thank you very much for talking to me today. I hope you enjoyed this discussion, and as usual, yes, just please follow if you like the other subjects. I'm sure there'll be more space because this is one of the focus of our podcast.
Thank you very much, Hannah, for your interest. Thanks to the audience for the interest, for listening until here. I'd be happy to report progress in the future.
Perfect. Thank you very much. So this is it for today. I hope you enjoyed the show and the very special interview with Dr. Jan Thoemel. If you did, or if you want to check out more, please follow us, subscribe, go to the usual social media channels, or just drop us an email. Remember that the best way to do that is just to go to the Buzzsprout website of our SciLux podcast. I'll be very happy to hear from you. And this is it. This was SciLux, and my name is Hanna Siemaszko.